I've talked about whole orbit data before, and Robert just talked about the 2017 Symposium. I talked about whole orbit data in the 2017 Symposium, but that was a long time ago. It had never been used before because Fox 1E and HuskySat hadn't flown. So this is a little bit of an update on whole orbit data, and so I want to explain to you how the whole orbit data algorithm works, and then what else we can do with a very similar algorithm. And on top of everything, by showing you this, I really want to encourage you to collect telemetry and send it to us. And you will see that we depend on you to get the whole orbit data. And of course, you can also download the whole orbit data for your own Fox2LM version. So what is whole orbit data? You can kind of see the point in this diagram. Satellites are going to orbit over the whole Earth, especially satellites that are in somewhat polar or sun-synchronous orbits. They orbit over the whole Earth, or you could also say the Earth turns under them, but there's a limited number of ground stations. That's especially true over the Pacific and Central Asia. So, there isn't too much here. Unfortunately, this particular picture doesn't show Europe. There's a lot of stations in Europe. And thank you to our European friends for collecting data for us too. Let me also point out this one right here. Where's that? Hawaii, right. We've got one member who has a home on the Big Island in Hawaii. We gave him a Fox in the box, and he has set it up. And so we do get some telemetry from the middle of the Pacific Ocean. We have a few people in Alaska, I think, and we talked to people at the poles as well, but I'm not sure if we actually have any working there or not. But anyway, the point is that there are lots of stations in Europe, some in India, some in the Indian Ocean, and that one in Hawaii. But there's a lot of places where there isn't any telemetry, and we would like to know what goes on. The processor reset over the Pacific. Why? What was the temperature getting too high? Radiation doses, or were we going over, the South Atlantic anomaly or something like that? So anyway, I do want to thank all the hams and non-hams for collecting data around the world, and I hope this will encourage you to do so too. But anyway, what is WOD? WOD means whole orbit data, and the point is, how do we get the data over locations that don't have ground stations, right? And the answer is we send a whole bunch of data as fast as we can when we are in range of a ground station, even though it was collected earlier in the orbit. But the satellite itself doesn't know where the ground stations are. It's not like each ground station sends a signal that says, hey, I'm here, you can start sending me data. So how do we do this? And the answer is we send that same data over and over and over and over again. All of our satellites since the early Foxes have had this stuff called MRAM, magnetoresistive something or other memory. It's a special kind of memory that is not very dense, but it is non-volatile. You can turn the power off, you can reset the processor, nothing gets lost. It has essentially infinite write cycles, unlike the SD card that you kind of see here. The SD cards do not have infinite write cycles, even if they're not in a radiation environment. But the MRAM does also have a fairly high tolerance to radiation. The older Foxes, the FM Foxes, used it for the voice of Fox. If you've ever heard Veronica and her downlink. This is Fox 1A. This is amateur radio station Fox 1A. That's her voice was digitized and put in MRAM. We also saved the min-max values there and have from the beginning. Since Fox 1E and HuskySat has also stored whole orbit data. And MRAM is organized for the whole orbit data as a circular buffer. We typically collect one data set for whole orbit data per minute and store it in MRAM. But you saw in the previous talk, we send a lot of data, of those data packets out of MRAM, so they are transmitted a lot faster. Now, unfortunately, we didn't get this to work. This was a great animation that works fine on a Mac. And what you see is that this is a circular buffer, and the right circle goes chunk, 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 and keeps writing into a slot in the circular buffer. The read pointer goes zoom, 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 zoom. So I think, for Fox 1E, we would send 31 whole orbit data packets per minute, but we only collected one. So every time we collect one, we wipe out the oldest of the previously collected ones. But now the question is, how much whole orbit data do we actually get to save, or should we save? How much space of whole orbit of MRAM should we use? And the answer is surprising. It was surprising to me totally. No matter how big the memory, we still transmit each whole orbit data packet the same number of times, because it relates to how fast we transmit versus how fast we write. Yes? But so why does it matter? Why don't we just have one slot or something, or 31? And consider, if we have a small amount of memory, a given packet is sent more frequently. So it's still sent the same number of times, but a lot more frequently. So it doesn't stay in MRAM as long, and thus what? It sees fewer ground stations. With more memory, a given packet is sent less frequently, but it's spread over a wider area on the Earth. So how much memory use is optimal? Carl Wick, N5MIM, was wonderful, and the actual math that he did in his simulation is in the 2017 proceedings. So if you want to look it up, you can. But it's great. He simulated this whole orbit data thing based on kind of guesses for what an orbit might look like, and it's typically a sun-synchronous orbit of some sort, and based on ground stations that we knew were typically sending us data. So he did that simulation. Turns out there actually is an answer, and the answer is approximately 42. No, 150. 150. If you send more, it doesn't hurt anything particularly, but it doesn't help much either, for the most part. So again, each saved whole orbit data packet payload gets sent the same number of times, regardless of memory size, but it's sent over a larger area. So note that 150 assumes the same number of ground stations that we have typically had. The number has gotten smaller as we've had fewer satellites in orbit that go to Foxtel-M. So I do want to encourage anybody to collect telemetry as soon as we have something to collect from. Yeah, go ahead. What's that? Yeah, it's intended not to be factorial, but oh, good point. So yeah, you can see the math that Chris did in the 2017 papers, and Fox 1 telemetry Fox 1E telemetry that Carl and I gave in that symposium. Yeah, 150 factorial, that would be a lot of packets. I don't think it would fit in MRAM. So before I go on, I just want to give it credits for the whole orbit data stuff. Carl Wick is amazing. He's a silent type. He doesn't say too much, but he'll hear, "Oh, how are we going to do this? We need something." And Kip can see this as well, and he'll just go off and he'll do something. He'll solve the problem in some fashion or another. So Carl did a wonderful job with this whole orbit data simulation. Chris Thompson, who is the FoxTelem writer, and FoxTelem needs to understand the whole orbit data algorithm too, because after all, you don't necessarily send all the packets in time order. So he has to sort the packets as they come in to make sure they're all in order. Mike McCann, K2 gigahertz, actually had the original idea for doing whole orbit data. So thanks to him. And I'm the one that did the FoxTelem, the telemetry transmissions. So thanks to me, I guess. Okay, so let me go on to, I wanted to talk about how whole orbit data works, because the point of this paper is I found another use for a very similar algorithm. So to talk about this new use, I first want to talk about how much data we need to downlink at different times for the life of Golf T, and what telemetry speeds we have and have to use. So I think I said before, Fox 1A through D at either 100 or 200 bits per second, depending on which slide you look at, data under voice. Fox 1E, HuskySat, MESAT, and so on, anything that uses LTM, including Golf T and Fox Plus, is 1200 bits per second BPSK. And as I said earlier, the amount of data that we collected for these guys didn't change much, so that's what we used that extra speed for, was to send whole orbit data. Golf satellites are a lot more complex. They're 3 times as big, but I think, as Jerry would say, 90 times as complicated. So there's, some health data that's probably a little similar, but then you have all of this stuff, like we have an ADCS, Attitude Determination and Control System, in the Golf T. And there's a lot of commissioning work we have to do. ADCS depends on the magnetic fields of the Earth and knowing where you are for a given magnetic field. So there's a lot of commissioning. You need to send down data that was received in the magnetic receivers. Jerry won't like me to say this, but I suppose we might sometime have future pictures. But there's a lot of data that could need to be sent down. So you might ask, why don't you just make telemetry faster? Well, we might in Golf 1 in the future thing. But right now, when we first changed this, when we first started, 1200 bits per second compared to the 100 bits per second of data under voice seemed enormous. So we started out doing what was easy to do with the 1200 bits per second. And that kind of baked into some hardware designs that 1200 BPSK. In addition, the LIHU probably could go a little faster, but not enormously faster. So the answer is, as long as we are using some of the legacy IHU hardware, we probably can't go much faster. We might change that. We might very well change that in future processors, future satellites, but not now. So what do we do? How do we deal with 1200 bits per second and larger data quantities? So let's think about how much data we actually need to send. For an example, for ADCS commissioning, we need raw magnetometer readings. Mentioned before, raw gyro readings, some coarse sun sensor data, and some of this data is collected every 10 seconds for an entire orbit. So, do the math, 90 minutes for an orbit, 66 groups of 10 seconds, it's a fair bit of data, and I didn't tell you how much data was in each packet that had to be collected. And one downlink frame is only 669 bytes. Right, so we don't have, but the other thing about this is we don't have to do it very often, and the data doesn't need to be there instantaneously, right? As long as the data is time-stamped, it doesn't need to be sent immediately when it was collected. So, for example, how do we get all this data from the ADCS? The ADCS unit that we're using actually has a non-volatile memory built into it. And it collects all of its data every 10 seconds regardless. And we just have to ask for it and save it on our own. So sort of a summary of requirements, right? We need to collect data frequently. There's a lot of it. We need to downlink it to sparsely loaded ground stations, but not necessarily immediately. Does this sound a little familiar? It's kind of like whole orbit data, isn't it? So I hope nobody, well, if you're a Mormon, I'm sorry I used LDS as the things here. No, honestly, I do apologize. But LDS I used as large data sets. So how does LDS differ from whole orbit data? LDS is a large quantity of data, but it's limited. So it just doesn't keep going forever. Whole orbit data is continuously collected. With LDS, we don't want to lose any data. We need all that data for the commissioning process. Whole orbit data, if we miss some, well, it's too bad, but it's not a tragedy. The LDS is only done a few times in the mission. Whole orbit data we'd like to do continuously for the entire mission. And LDS, the amount that we're collecting fits into MRAM, but whole orbit data over the life of the satellite is far greater than the total MRAM size. So then the question is, can we modify the whole orbit data algorithm to accommodate these differences? And I wouldn't be here if the answer didn't seem to be yes. So here's how I plan to downlink LDS. And by the way, this is implemented, partly tested on my flat side. It works. So sorry again, I can't run this nice little animation that I had. But the idea is that you write frame-sized chunks of data from the ADCS or wherever it's coming from into MRAM, including a timestamp when it was collected. The amount written has to be less than is available in MRAM, so there's no overwriting. It's just a chunk in MRAM, and that's what we want to downlink. So we collect and write it just once, and when it's done writing, we treat, again, the data as a circular buffer to read from and transmit that same list of data over and over and over and over and over again. The difference between that and WAD is that we never do any more writing until it's commanded to. So we're just sending the same data over and over again. On the ground side, Fox2Lem is, again, very clever about taking time-stamped data and putting it in the correct order. So Fox2Lem to Fox2Lem, LDS looks identical to WAD. It didn't have to do anything different, except that, thank you, Chris. He had to tell me how to make another tab that was that looked like whole orbit data. So it requires adding new payloads, new tabs with WAD-like data, and turns out that was actually pretty easy to do. So But remember, the ground stations are sparse. Even if everybody here and every member of AMSAT collected telemetry, oh my God, that would be wonderful. There would still be lots of holes. And so how do we deal with holes? Surely we're going to miss some LDS packets. And it's important for LDS. So we could keep sending everything over and over and over and over again. But if we only have 2 or 3 packets missing, do we really want to send 100 packets over and over again? No, that would take a long time. So the solution is that I implemented an uplink command. And the uplink command has the capability of giving 2 different sections of that data and say only send data between here and here, between A and B, and C and D. So in the example here, which you can't see because it doesn't run, I could command it to only send the missing range. So for example, I could tell it only transmit between 6 and 7 and between 9 and 10. And so it never transmits the other ones, all of the other data in MRAM. It doesn't erase it, it just doesn't transmit it, it just skips around. So the idea is that we fill in those holes much more quickly. So the summary of LDS is we can collect many thousands of bytes quickly and then send them slowly in small time-stamped chunks. And we repeat sending over and over until most get received. And then we can, when the satellite next goes over a ground station, we can send a command to transmit either only or mostly the missing pieces. And then it's finally done, and hooray, we've got all the data that we need, and now we can send a command for the next thing we need. If we were collecting magnetometer data, we can now tell it to collect gyro data and repeat the entire thing. And then when we get enough information, we can go into the next step of the commissioning of the ADCS. Okay, my rocket porn. I think it's fair to say a lot of the things that we do, like this LDS algorithm, are workarounds for capabilities we don't have, right? That's life, building satellites as volunteers. But, you know, I'd argue that's also life as a ham. I mean, how many of us, I suspect only a few of us, don't have workarounds that we've invented in our shacks. So, you know, it's kind of too bad we have to do this sort of thing, but that's the way it goes for the next satellite, and maybe we can improve things on the one following that. So let me add again, thanks for getting Foxtel M. Thanks for putting it on your Mac or your Linux box or anything else. That, you know, a Fox in the box, that data is just so important to AMSAT engineering, for engineering and at the commanding stations. So yeah, there's no, oh, where did you go? There we go. So yeah, this is not an amateur radio satellite launching. It's the next to the last space shuttle launch, which, and I took this picture. I was there at Kennedy Space Center. Space shuttle is just the coolest thing to see. Anyway, so thank you very much for listening. If you have any more questions about LDS or whole orbit data, feel free.
Any questions?
Yeah, heads up first.
Given your ability to fill holes, is that going to be an automated process that your system will figure out what the holes are and then automatically set up, or do you have to manually make that command?
You have to manually make it. We don't really have any automatic uplink of any sort for our satellites.
So will this be a command station responsibility or
Yes.
an engineering station?
Well, I mean, to be honest, for Fox T, for Golf T, sorry, I think there's negotiation to be done between the ground stations and engineering as to exactly who does what and when.
Do you want an answer now?
If
No,
you
I'm
like.
kidding. I'm kidding. I'm kidding. I was pondering the same thing, Barry. Thanks, Burns. Always informative, and we know the value of whole orbit data. And those of you that haven't looked at some of the number, there are millions of frames of data that have been collected from the various Fox satellites. My question is it's sort of an old reflection that at one point, a couple of our birds did have a 9600 baud
Yeah.
mode. So why going forward aren't we doing something like that again?
I think the answer is that we knew how to do the 9600 baud with an FM transmitter. And to be honest, I never liked that mode because if you look on the spectrum analysis, it's splattered all over the place. So I think if anybody really paid attention, there might be some issues there. But I think the real answer is that we knew how to do it with FM. It takes up a huge bandwidth, so it's not gonna work nearly as well on a linear transponder.
Any plans to ever run a file system so you can just ask for the file to be downloaded?
I'm glad you asked that. Mike is here to talk about Fox Plus, and there is some possibility of another Fox Plus having more packetized data. So I'll let Mike answer that question. Or I'll let Mike answer the question when he gives his talk.
Any more questions? All right. Burns, I just want to thank you for putting together the Fox in a Box thing. You made it so easy for people to set up home stations that there's no excuse why they don't.
So I have to say that Alan contributed hugely, Chris contributed hugely to the Fox in a Box. But yes, it's easy to put together. Get one. If you have a Raspberry Pi, you can download the software for free. So do it.
Burns, I will say, it's so easy, even the AMSAT president can do it.
Yeah, that's right. You did, didn't you? How many calls did I get about that? Thank you.